Hi everyone and welcome back to my channel in Economist. So today's video is going to be very important because we'll be discussing a couple of very important points about multicollinearity in today's video. This is going to be part 2 of multicollinearity. If you haven't watched my previous video, please check that out because there I have explained what is the concept of multicollinearity and what are the consequences, right? So in today's video, what we will see is that firstly, if the multicollinearity is perfect, I hope you remember from the previous video, I have distinguished between what is perfect multicollinearity and what is less than perfect multicollinearity. So there I have said that in reality, perfect multicollinearity has severe consequences, right? I have explained that perfect multicollinearity is very rare in real life scenario and we will focus only on less than perfect multicollinearity. So in this video, we'll be explaining why perfect multicollinearity is having severe consequences, right? If multicollinearity is perfect in nature and if it is present in your model, what will be the severe consequences for that? So this is going to be the first part of this video. Then in the next part, we will see how to detect multicollinearity. What will be the methods that we use generally for detecting multicollinearity? And finally, we will touch upon the processes that we can use to handle multicollinearity. If we see that yes, multicollinearity is present in your model, then how do you handle, how do you deal with this multicollinearity in your model? And everything will be discussed in this particular video. So please stick to the end of this video and I hope that multicollinearity will be very simple for you if you see this video till the very end. So let's start. So firstly, we will see what happens if multicollinearity is perfect. So let us consider a model. So while discussing multicollinearity, we always take at least 3 variable or 2 variable models. For example, this is the model. 2 variable means there should be 2 independent variables. Here what we will see, the model is something like this. Beta 1 plus beta 2 x2I plus beta 3 x3I plus ui for all I from 1 to n, right? So in this model, altogether you have 3 variables. One is the dependent variable yi and you have 2 independent variables x2I and x3I. So this is altogether a 3 variable model where you have 2 explanatory variables x2I and x3I. So this is a 3 variable model. Now what happens if you take the average of this? If you take the average of this, though I haven't done this in MLRM model is not yet done. I'll be starting that in the next video. But as of now, just see the process, what you have to do. If you take the average of this dependent variable, then what will be this side? This side you will have something like this. X2 bar, beta 3 x3 bar, and then you have plus u bar. This is what you will get. This is from the first normal equation of the multiple linear regression model that I will be doing in the very next video, right? So this is what you will get if you take the average from the first normal equation. Now, what we will do, we will take the deviation form. Take the deviation form. What will be the deviation form? Simply take yi minus y bar. So here you have, this is the first original model. And this is what we got from the normal equation. Now, if you subtract 1 minus 2, basically we are doing 1 minus 2. So yi minus y bar, this will be simply, this beta 1 will cancel out. Beta 1 will not be in the picture. So beta 2, then you have x2I minus x2 bar. Then if you take beta 3 common, you will be having x3I minus x3 bar plus ui minus u bar for all I, right? Now this we can express in another form. If you remember, yi minus y bar can be written as small yi. In the deviation form, all the variables are written in a smaller letters basically. Not in the capital letters, but in the small letters using the small keys. So yi minus y bar will be simply this capital yi minus capital y bar will be simply small yi. Then you have beta 2 then you have x2i, small x2i. So this x2i minus x2i will be small x2i. Plus you have beta 3, small x3i. And plus you will have, suppose this is bi, where this bi will be simply ui minus u1, right? So this is the ultimate model that we reduced from our original model. Can you see that? Can you observe this? I hope this much is absolutely clear. So from the original model, we have derived something called the model in the deviation form. What is the model in the deviation form? Here you have small yi on the left hand side, and then on the right hand side, you have these two variables in the deviation form, and this is the model in the deviation form. Now, why did I do this? We have done this because we will apply the OLS method on this new deviation form model. We will not work with the original model that is given to us here. When I do the multiple linear regression model, we will again be doing this kind of a thing. We will, apply OLS there. And if you apply OLS there, what you will get? You will get the formula for finding out beta 2 cap and beta 3 cap, right? If you apply OLS on this particular deviation form, if you apply OLS method, least square method, ordinary least square method on this deviation form, you will get the absolute formula for beta 2 cap and beta 3 cap. For this video, I'm directly writing the formula because I haven't derived it earlier. We will derive it. But as of now, just take it from me that this will be the formula. I know it's a long formula, but this is how it is. Let me write it down. Summation I from 1 to n yi x to I into summation I from 1 to n, then you have x3i square minus summation I from 1 to n yi x3i into summation I from 1 to n x2i x3i whole divided by summation I from 1 to n x2i square summation I from 1 to n x3i square minus summation I from 1 to n x2i x3i and a whole square of that. So this is the particular formula that you will get for beta 2 cap. This is the slope parameter. This is the slope parameter which is associated with the explanatory variable x2i, right? So if you apply OLS in this deviation form of the original model, then you can deduce simply this particular formula. And here see all the x2i's and x3i's are in the deviation form. So the entire formula is in the deviation form, and that is what we will be using, right? So this is the estimation of beta 2 cap. The process of derivation, again, I'm saying it will be done in the very next video. So stay tuned for that. As of now, please see, this will be the formula. And I'll show you why I am doing this here. So this will be summation yi x3i into summation I from 1 to n x2i square minus I from 1 to n. This will be x2i square summation I from 1 to n yi small x2i and whole divided by this will be summation I from 1 to n x2i square. The denominator is exactly the same. Summation I from 1 to n x3i square summation I from 1 to n x2i x3i whole square, right? So this is the estimated value of beta 2 cap and this is the estimated value of beta 3 cap. Now you will see why I have done this. So under perfect multicollinearity, in the presence of perfect multicollinearity, what we can say is that our explanatory variables, that is x2i and x3i, will be perfectly or linearly related with each other. If you remember from my previous video, so what we can write is that x3i will be some lambda times x2i for all I, and where this lambda should be strictly not equals to 0 and it's a constant. It's a constant, right? I hope this point is clear that in the presence of perfect multicollinearity, if you have perfect multicollinearity, then you will have a perfect relationship or perfect linear relationship between x2i and x3i. What will be the relationship? X3i will be some linear combination of x2i. Here it is lambda x2i for all I. And where this lambda is a scalar quantity. Lambda is strictly not equals to 0 and it's a scalar quantity is simply a constant. So for example, if the lambda value, suppose lambda value is 2, what does this mean? If you take the variables x2 and x3 here, so if x2 value is 5, x3 value will be simply 10. If it is 6, it will be simply 12. If it is 10, it will be simply 20, right? So in this fashion, we are moving forward, right? If you put x2 equals to 5 and lambda value is 2, is a constant, is a scalar value, then this will be the relationship. X3 will be simply 2xi, right? X3 will be simply twice of x2. So this is the kind of relationship that we are talking about, right? Now, if this is the case, what we can do, let me remove this portion. You can simply substitute this relationship back into this particular formula that we have used, right? We can simply substitute this in the formula that we have used. So what we will do, let me do that. So what will be beta 2 cap? What will be beta 2 cap now? So beta 2 cap will be simply summation I from 1 to n. This yi x2i will be the same. But now what you can do, instead of x3i, see here you have x3i. Instead of x3i, you can put this formula because here this form will be, whole for the deviation form as well. So you are simply, if you subtract this x3 minus x3 bar, and here also if you subtract this x2i minus x2 bar, so this relationship will still hold. So this is simply small x3i is lambda small x2i squared. This can be written from here. I haven't wrote that, but this is very much understandable from this formula, that from here you can write x3i will be small x2i. This relationship will also hold because from the original form, you can simply find out this deviation form by subtracting x3 bar on the left hand side and x2 bar from the right hand side, right? So this thing will hold. Now, if this thing holds, then you can simply write in this way. Instead of x3i here, you can substitute lambda x2i and the whole square of that. So let's do that. This will be simply lambda squared x2i squared, right? Minus summation I from 1 to n. Here you will have yi, then x3i will be lambda x2i, and then summation I from 1 to n, x2i, x3i. x2i will be as it is, x3i will be lambda x2i. So I want each of you who is watching this video to write on your own. I am not giving you this lecture PPTs because I want you to write on your own, because that is the only way to learn econometrics. If I write everything, that will not going to help you. You have to do it on your own. You have to write on your own to understand all these things that I am doing, right? I know it's a little hard, but that is the only way you can learn econometrics. Please take a pen and a notebook and please write it on your own. And that is when you will understand what I am doing. So I am basically just substituting wherever I have x3i, wherever I have x3i, I am just substituting lambda x2i. Here also and here also I will do the same thing, right? Here and here I'll do the same thing. So let's do that. So here x2i, here have I done the right formula? Let me check. So here I have made a mistake. So let me just a minute. For what you will have, minus summation I from 1 to n, it will be yi x2i, and then summation I from 1 to n x2i x3i, right? This will be the formula, right? This is the formula. Now here you will have x3i and here you will have x3i, and we will substitute that. So let's do it. In the denominator, what you will have? In the denominator, you will have summation I from 1 to n x2i square summation I from 1 to n lambda square x2i square I from 1 to n x2i, and then you have lambda x2i and the whole square of that. So once you substitute this thing from what we got from perfect multicollinearity, this will be this expression. Now you can simplify. See, here you have lambda square, and here you will also have a lambda square. Lambda from here, lambda from here. So lambda square will come out. So beta 2 cap will be lambda square and summation I from 1 to n. This will be yi x2i. Summation I from 1 to n x2i square. Summation I from 1 to n yi x2i summation x2i square, right? And in the denominator, you can also take out lambda square. See here you have lambda square, and here also you have lambda square. So take that out. You take the lambda square out, what will you get? You will be getting summation I from 1 to n x2i square. This portion is not changing, and then from the next portion, you will again get the same. See, here you have summation x2i square, and here you have summation, okay, summation x2i whole square. Summation x2i, okay, let me, so this will be summation x2i whole square, and then again summation x2i whole square. See, from this particular expression, I have only, so see this first expression, I have taken lambda square out. So here you have summation I from 1 to n x2i whole square and a whole square of that as well, because here you have one term, here you have another term. So x2i square whole square. This is what the first term I have written. Here it will be a square. And in the second term also, if you take out lambda square, so lambda comes out and here is a square. So lambda square comes out, and then you have summation x2i square and the whole square of that as well. So this particular thing. Now, can you say anything about this particular expression? What will be this expression? Can you see this? I hope you can see this. Lambda is not equals to 0. This is what we assume. This is a scalar. So this lambda square is gone. Now what can you say about the numerator and the denominator? If you see carefully, if you pause the video and think, you will see this is exactly the same equation. This is exactly the same component. See, the first component is the same, second component is the same. And the denominator also, the first and the second component is exactly the same. Can you see this? Can you see this thing? If lambda square and lambda square is gone, the numerator and the denominator is exactly the same. So this is a minus a, this is b minus b. So this is exactly 0. So beta 2 cap is simply in the 0 by 0 format, which is an indeterminate form. Which is an indeterminate form, right? 0 by 0 is an indeterminate form. We cannot work with this kind of an expression. Right? We cannot work with this kind of an expression. The similar thing this can be shown using beta 3 cap. I want to give you this as your homework. Please do this on your own. That in beta 3 cap, use the same expression. Use the same expression. Instead of x3i, put lambda into x2i here, 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 here. Right? In these four places, instead of x3i, put lambda x2i and show that this will also come out to be in a 0 by 0 format, right? If you do this, this will also be in the 0 by 0 format, which is also an indeterminate form. So this is the severity or the consequence of presence of perfect multicollinearity, right? This is the severity or the consequence of perfect multicollinearity that we cannot estimate beta 2 cap and beta 3 cap individually. The individual effect of the coefficients, that is individual significance or individual effect of the explanatory variables, cannot be found out, because see, beta 2 cap is what? Beta 2 cap is simply, from this expression, beta 2 cap is the effect of x2i when x3i is kept constant, and beta 3i is the individual effect of the variable x3i on yi when x2i is kept constant. But here what we see is that under multicollinearity, you cannot keep constant one of the variables. So if you change x2i, x3i will automatically change. If you change x3i, x2i will automatically change. So you cannot find out the individual effects of each of the explanatory variable on the dependent variable yi, and only the joint dependency, only the joint effect can be found out, right? This is the problem with perfect multicollinearity in your model. So let me write everything. Let me conclude. We know that beta 2 cap gives the change in the average value of y, in the average value of the dependent variable y when x2 changes by 1 unit, keeping x3 as a constant, right? Keeping x3 as a constant. Now, under perfect multicollinearity, I'm not writing it, multicollinearity, there is no way x3 can be kept constant. X3 can be kept constant because in this case, as x2 changes, x3 also changes by a factor lambda, and so we cannot get individual effect. We cannot get individual effect or separate effect of x2 and x3 from the given sample, right? So this you can consider as a summary of everything that we have done so far, right? So what I have said is that beta 2 cap, as I have told you, this is the definition of beta 2 cap. It gives the change in the average value of y when x2 changes by 1 unit, keeping x3 a constant at a constant level. But if the multicollinearity is perfect, so there is a linear relationship between x2 and x3, exact linear relationship. That is why there is no way when x3 can be kept constant, because in this case, as x2 changes, x3 will also change by a factor lambda. And so we cannot get individual effect or separate effect of x2 and x3 from the given sample, right? So this is our part 1 of this video, where we have explained what happens if multicollinearity is perfect. Now let's move to the second part, where we will see how to detect multicollinearity. There are several ways we can do this, but this first method is the most commonly used method, which is the variance inflation factor or variance inflating factor, which is known as VIF. This is the most commonly used method we use for detecting multicollinearity. What is VIF? VIF measures how much the variance of the regression coefficient increases due to multicollinearity. So basically, variance of beta 2 cap is inflated under multicollinearity, and variance of beta 3 cap is also inflated if multicollinearity is present. So this variance inflation factor measures how much this variance of this coefficients, regression coefficients, namely beta 2 cap and beta 3 cap, is inflated due to multicollinearity, and that gives you a measure of detecting multicollinearity. A high variance inflating factor, typically greater than 5 or 10. Usually we say variance VIF is, if it is greater than 10, then it's a serious problem. It's a serious threat to the regression that we are using. But if it is still greater than 5, we can say that multicollinearity is present in your model. And this is the basically the thumb rule. This is the interpretation of the thumb rule. If VIF is less than 5, then we say low multicollinearity and it is acceptable. We can still work with such a model which has a VIF of less than 5. But if it is greater than 5, we will say that moderate multicollinearity exists and it's a caution. And if variance inflation factor is greater than 10, then it will be high multicollinearity and then serious problem begins in the model, right? So this is the interpretation. Now let me give you the formula. If your model looks something like this, yi is beta 1 plus beta 2 x2i plus beta 3 x3i plus ui. Suppose this is your model for all I. Now, what will be variance? What will be variance of beta 2 cap? If you remember, I have, while talking about the consequences also, I have mentioned this formula. I am not deriving it. I will be deriving it in the next video, as I have told you. This is a portion of multiple linear regression. I'm just giving you the formula to explain how to see the VIF. This, and then you have 1 minus R23 square. This was the formula. So here what we can say, this is simply sigma square summation I from 1 to n small x2i square, and the remaining portion what you have is known as the VIF. See, so this is sigma square and this portion can be written as small x2i square. This is again in the deviation form. Sorry, this will be square. This will be square, and then everything rest of the part is known as the VIF. So what is VIF? VIF is simply 1 upon 1 minus R23 square, where R23 is simply the correlation, between x2 and x3. Right? This is simply the correlation between x2 and x. So this is the VIF. This is the VIF, and also you can do this for the other variable. Let me show you variance of beta 3 cap. This will be sigma square summation x3i square, and then the rest of the portion 1 minus R23 square. So again, sigma square summation x3i square, and then the rest of the portion will be again VIF. So here also, this is 1 upon 1 minus R23 square, where R23 is the correlation between x2 and x3. And higher the value of VIF, the stronger the multicollinearities. Typically, when we see that if this R square value is suppose say greater than 9, then only we see that this VIF is greater than 10. This is also a rule of thumb. You can use this thing for your situation. So you can see when the correlation between x2 and x3, that is R square basically, if this correlation value is greater than 0.9, if this is greater than 0.9 or 0.8, that is, it is on the higher side. If this is the case, then we will see that VIF is greater than 10, and this will give you an indication that multicollinearity is present, right? So this is the mostly used approach for detecting multicollinearity. Also, you have some other methods. For example, the correlation matrix. So correlation matrix check the pairwise correlation, right? So suppose instead of two variable, you have, suppose explanatory variables are x2, x1, x2, x3, x4, x5. Suppose you have 5 independent variables in your model. So in correlation matrix, what you do, you find out the pairwise correlation of each of this. You find out the correlation coefficient of each of these variables, and if you see that this pairwise correlation is very high, suppose it is 0.8 or 0.9, right? All this pairwise correlation, if you see they are very high, then they might be, it indicates that the independent variables are correlated with each other, and we'll say multicollinearity is present in your model, right? So this is also another approach. This is mostly used for more than 3 variables, more than 3 variables. This is a handy method, but still VIF can be also used for this approach as well. So correlation matrix, if not mostly used, VIF is the most commonly used measure. So this is another way. Then you have tolerance method. Tolerance is just another matrix which is the reverse of the VIF. So tolerance is 1 upon VIF. So we have said that the stronger the VIF, more strong the multicollinearity is. But if you reverse it, then we will say the tolerance, the lesser it is, the stronger will be multicollinearity, right? since it is just the reverse of DIF, so if the tolerance is less than 0.2 or 0.1, then we will say severe multicollinearity exists in your model. Also, you have some other approach. This is mostly used when we do the matrix form, when we analyze everything in the matrix form. That is also what we will cover when I make advanced econometrics playlist. That will be in my timeline. I'll make that playlist also very soon, just right after making this series. So stay tuned for that. So there I'll explain the eigenvalue and the condition index. This method is mostly used there. So compute the eigenvalue for the correlation in matrix that we have talked about. So this is the correlation matrix that we have talked about. So you have to compute the eigenvalues and then you have to compute this particular matrix. Condition index means root over of largest index value upon the smallest index value, or sorry, eigenvalue. So this is generally not required for your undergraduate level, but when you go to postgraduate or PhD coursework, courses, then you will need this kind of method. And they need separate videos. I'll be covering all these things when I'll be going into the advanced econometrics playlist. So stay tuned. And if you calculate this metric and if you see that it is greater than 30, then you will say serious multicollinearity again exists in your model. Finally, you have two more detection methods. They are also sometimes used. Regression diagnostic run auxiliary regression. Auxiliary means what? Each independent variable is regressed on all the other variables. And if R square is very high in this regression, we will say that multicollinearity exists. So this is also another approach. And also, this is also a very important approach, which is the principal component analysis. Again, I'll be covering this when I go into the advanced econometrics, where what we do, PCA can be used to reduce the dimensionality. This is basically a method of handling multicollinearity. You can detect also and you can handle also using principal components. So this can be used to reduce dimensionality, to detect patterns of multicollinearity. Here what we do, some components explain most of the variance. We will suggest that the original variables are highly collinear. Again, I am not going into the depth of the process because I'll be making separate videos for each of this. And finally, closing remarks, how to handle multicollinearity. So we have so far discussed what will be the concept, what are the consequences, what will be the problems associated, and how to detect that. The final thing that we have to know, how to handle multicollinearity. If multicollinearity is present, what should you do? So there are these 5 steps that you can follow. Firstly, remove the highly correlated variables. So if you have this, suppose x1, x2, x3, x4, 4 variables, independent variables, and you see that x2 and x3, they are highly correlated. So simply drop one of those variables, right? Simply drop one of those variables, and this can be done using feature selection. So if you do that, there can be arising problems of omitting variables. Suppose x3 is a significant variable, but you are dropping that out. So there is another concept called omission of variable or inclusion of irrelevant variable. They are separate chapters. Specification bias is a separate chapter. I'll be doing that. But this is one of the ways in which you can handle multicollinearity. Suppose two variables are correlated, highly correlated. So simply drop one of the variables out. This is the first method of handling multicollinearity. The second method says combine collinear variables into a single factor, what we do in PCA, principal component analysis. As I have told you, principal component analysis works both the ways. It helps you to detect multicollinearity also it gives you the tool to handle multicollinearity, where what we do, we combine the correlated variable into a single variable or single factor. Also, there are other methods. Ridge regression can be used. Lasso regression, ridge regression or lasso regression can be used, which is L2 regularization, which shrinks the coefficients. Or you can use the sample size method. If sample size is increased, then the dependency will automatically reduce. For large sample, this dependency among the variables automatically reduces. So you can use that. Also, you can standardize the variables to reduce multicollinearity, right? So these are the 5 methods that you can do to handle multicollinearity. And that is all from my side for today. If you have any questions anywhere, if you find anything hard to understand, you can let me know in the comment section. And if you find this video helpful, please give me a like and do subscribe to this channel, AN Economist, and I'll keep making these useful videos for you. And in the next video, I'll be starting off with the multiple linear regression model. And once I finish that, I'll be covering the advanced econometrics as well, where I'll cover everything that I have talked about while taking this lecture, right? So thank you so much for your time and stay tuned for the next video.